In this part, we want to look at a different application of linear algebra, in particular an application to network flows. So first of all, let me define what a network is. A network consists of a collection of points called junctions, or sometimes nodes, with lines or arcs called branches connecting the junctions. So let me just draw you an example of something that would be a network. So we have a bunch of nodes, okay, and we have lines connecting them. And we have directions on each of the particular lines. So information comes in this way, something comes along this way, it comes to a point, and let's label our points. Here we have A, B, and C. So things coming along this line come to the junction C and they can split. Some of the information can go in this direction, some of the information can go in this, whatever we're modeling. And then when it comes to B, it decides to go this way, and everything kind of leaves the network over here. So the arrows here denote the direction that you're allowed to travel in the direction of the flow. So arrows denote the flow direction. So you could think of this as modeling something like one-way streets, or you can measure maybe electricity moving in circuits. So you could probably think of some of the examples of your own of where you might see a network. Now there's some basic assumptions with a network. Okay, so basically the total flow into the network, so the amount of stuff coming into the network, well, that should definitely be equal to the flow out of the network. We don't lose anything once it goes into a network. So total flow out of a network. And then the same sort of reasoning we should have for a junction. The amount of stuff coming into a junction should be the amount of material flowing out of the junction. So the total flow out of a junction. So we have this network, some basic assumptions, and let me just give you kind of a small example of this with some actual numbers. Let's say I have one node and I have two branches coming out of it in this direction, and I have a branch going into that junction. And suppose that I have 100 units going in. 100 units in. We're not sure what this is. It could be electricity, it could be water, it could be cars, depending upon what you're modeling. And x1 of those units end over in this part, and x2 of these units end over here. So what you get is this total network here tells me that 100 has to be equal to x1 plus x2, because I'm doing the total flow into the network. So into, and then this part here is out of, the amount that goes out of. So we're getting a linear equation, right? So let me highlight that here. We get a linear equation. And this idea kind of generalizes. We're given a network with some information, and we're going to set up a series of linear equations, and then we can use linear algebra to solve it. So that's kind of what I've described here. Here's a typical problem. Given a network with some partial information to describe the flow at each branch. So here would be kind of a little bit more complicated example. I know the total flow out is 80 units over here and 20 units over here. I don't know how much is coming into the network, but once it comes in, x2 gets sent this way, x3 of those units get sent over here, and x1 units get sent over here. So before we kind of tackle this problem, I want to give you a chance to see if you can answer it. So what we want to do is set this problem up as a system of linear equations. So I'll leave that to you for a minute, and after the break, we'll come back and we'll set up the system of linear equations, and then we'll solve it.